Gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers from the Office of Public Outreach. And when you came in tonight, hopefully you got a new lithograph. This is the first time we've given out this lithograph. It's brand new this year. It is of the Triangulum Galaxy, also known as M33, also known as the third largest galaxy in our local group. Our local group has the Milky Way and Andromeda as two large-sized galaxies. M33 is a medium-sized galaxy, okay? And then everything else in the local group is just flotsam and jetsam dwarf galaxies. So this is the third important galaxy in our local group. This image, I gotta say, is so incredible you can't tell from the lithograph because it's a really, really detailed map of the stars in the Triangulum Galaxy, okay? We did the FAT survey, which went incredibly deep into the Andromeda Galaxy. This is the similar survey to go really deep and look at the stellar populations in the Triangulum Galaxy. So flip over on the back and that describes some of the things about what we can see in this amazingly detailed image that are so many more pixels than we could possibly put onto a lithograph. Actually, we blew this up to 12, 15 feet wide in order to see all the pixels, okay? That's how detailed this image really is. You can go online and get all the pixels if you would like. Yes, another reminder to silence your electronics, making sure it's both the phone, the text, and the camera clicks, okay? All right, tonight, red and brown dwarfs, understanding our smallest and closest substellar neighbors. I've been looking forward to this talk because these are the guys that really matter, okay? All the big bright stars that get all the attention, I think these are the stuff that really matter. Serge Dieterich will talk about that. Upcoming, in January, we have the AAS meeting the first week of January, and we have, of course, New Year's. So we are not going until the second Tuesday, January 14th, okay? January 14th, second Tuesday, Nimisha Kumari will be talking Cloudy with a Chance of Stars. So this is just the general life of an astronomer who's observing, right? It's cloudy with a chance of stars. I'm not exactly sure what she's talking about. She hasn't given me an abstract, but it sounds wonderful to me. February 4th is to be announced. I'll have that done by January. And in March, we have Nestor Espinoza talking about exoplanets, a search for new worlds. Now, for January, February, and March, you must know that those coming in live, the building will be under construction. The lobby is going to undergo a redesign, okay? Most of the building will be all just normal. It's just the lobby is going to have a total redesign. Strip it down, build it back up, okay? Which means that you probably won't be able to walk through the lobby to get into this thing. There will probably be an alternate entrance. There will be signs posted, okay? So next month, February, March, look for the signs to see where you're supposed to enter, okay? If you need wheelchair access, let us know because this is the wheelchair ramp to get into here. They said they can set it up and make sure it works, but if you let us know in advance, that will help us prepare for that, okay? And all right, our website for the upcoming lectures and other things is stsci.edu/public-lectures. Easy for me to remember because some of the times we've had much longer URLs here. So we have lists to our webcasts both on YouTube. Let's see, I got my spotlight remote here. There we go. Both our YouTube playlist and our webcast archives. We have been doing webcasting since 2005, so that's 14 years of astronomical goodness for you to explore. People like to binge watch. Hey, let's binge watch astronomy. If you would like notices about things, we have our lecture announcements. You can enter your email address here, hit that button, subscribe, and you will get once a month or twice a month emails about what's coming up on our lecture series. We also have lists of the upcoming lectures, and for each lecture, we have the details of it with the links to the STSCI webcast up here and the YouTube webcast down here, okay? For email, I talked about the announcements. It's easiest to sign up at the website, but there are always people who don't want to sign up at the website and want to hand me a piece of paper. That's fine as well. I can handle paper. If you have comments or questions, you can send them to publiclecture@stsci.edu. If you would like follow us on social media, we're on Facebook and Twitter and YouTube and Instagram. I myself am on Facebook and Twitter every now and then. Please do your social media thing as you like. There will be no observatory after the lecture tonight. The prediction was for very cloudy weather, so they canceled it. However, as I note that there are open houses on Friday evenings. On the Maryland Space Grant Consortium website, right here, the observatory status. Every Friday evening by 5 or 6 p.m., it's updated as to whether they will be open on Fridays. So you can come and go up there and enjoy the observatories the nights that they are open. All right? So now our news from the universe for December 2019. First, a Borisov update. It's still fuzzy. All right, so what is Borisov? Some of you may not remember. It is the second interstellar object that we have seen come through the solar system, or that we have identified coming through the solar system. You can see here that it was originally called C 2019 Q4 Borisov. All right, but it is now officially designated down here in the corner as 2I 2019 Q Borisov. The C was a provisional designation. The 2I says it's the second interstellar object. Here you can see its path coming down through the plane of the solar system and shooting past. It's moving at a tremendous speed, so fast that the sun's gravity cannot hold on to it, okay? It's moving at least twice as fast, and so it has escape velocity from the solar system. So this is a one and done, comes through the solar system, goodbye, it's just zooming past. All right, it shows us that things from interstellar space do come through our solar system, all right? And last month, I showed you the picture of that Hubble got of Borisov on October 12th. And I said, well, you know, this is a very clear picture of a fuzzy object, all right? That was Hubble last month. This month, we go to a picture from the Keck telescope, and it's still fuzzy. Now, Keck, of course, is a ground-based telescope. Although it's a 10-meter telescope and has greater light-gathering power than Hubble, it is still, of course, on the ground, and it doesn't have as clear resolution. But one of the things, since they have greater light-gathering power, it can get a lot more of the tail. And so they also produce this image showing the Earth to scale. Yeah, that tail is really, really, really long. The tail of this comet is approximately 100,000 kilometers long. But they estimate that the comet nucleus itself, the ice ball that's actually spewing off all this gas and dust, is only about a kilometer, okay? So the tail is 100,000 kilometers. The ice ball is about 1 kilometer. We're never going to see that, okay? It's always going to be a fuzzy thing, okay? Unless you fly up to it, you're not going to be able to see that small little ice ball in there. So all of it will be that way. All right, so the coming attractions for this weekend, it hits perihelion 5 days from now. It will be 300 million kilometers from the sun. Perigee is on December 28th. It will be 290 million kilometers from Earth. So it never gets really close to either the sun or Earth, or actually any planet for that matter. But it will be observable through late 2020, and when we get the studies and look at them, and we might be able to tell its size, shape, composition, perhaps its rotation speed, and other things about it. So we look forward to finding more about it. But you know, the next couple weeks might be really interesting because that's when it will be closest to the sun. The gases will be evaporating the most. Right now, the word is it looks pretty much like any other comet. It's hardly distinguishable from a normal solar system comet. That's what I've heard. Have you heard anything else, Serge?
I have not.
No.
But I have not followed it.
Yeah. So, although it's interstellar, it seems to be, so far, pretty normal. Okay? All right. Our second story, Raiders of the Lensed Arcs. Yes, I have no shame in the puns I will try and pull out, okay? All right, so galaxies. Galaxies come in these giant clusters. This is the Hercules cluster consisting of about 100, 200 galaxies. These galaxies can pile together, not just in tens and hundreds, but even in the thousands. And when you get a lot of galaxies together, they pull together and they have a tremendous mass. Now, for those of you who took your general relativity class in elementary school, mass warps space, okay? You put a ton of mass together, it warps the space, and then the light traveling through warped space changes, okay? All right, and we see that in the most massive galaxy clusters. So here, for example, is Abell S1063. And there's so much mass in this galaxy cluster, the space is really warped. And then you can see these streaks here, all right? And those don't look like normal galaxies. Well, they aren't. No, well, actually, they are normal galaxies, but the light has been stretched due to gravitational lensing. So a normal galaxy's light comes through this warped space. It comes out as this streak. We call these gravitationally lensed arcs, okay? Hence the Raiders of the Lensed Arcs, all right? There we go. So these are lensed arcs, and these lensed arcs can have some really interesting configurations. For example, here is Abell 370, a very massive galaxy cluster, and you can look over here on the right side and see this very interesting arc over here. Let me blow it up for you. This has been nicknamed the Dragon, as you might tell by the shape of it. And you can see that it's a very long and sinewy type shape. But what it really is actually multiple images of the same galaxy. So for example, down at the bottom here, you can see what looks like a galaxy, and then you can sort of see the same sort of structure and colors up here, and the same sort of structures and colors up here. I'm told that there may be like 4 different images of the same galaxy in this one arc, which is kind of cool, all right? That, you know, the gravitational disturbance, the warping of space so much is that the light from one galaxy passes 4 different ways through the warp space around the cluster. But that's not all. So if you go after it, you can really get something really cool. And this is what we had a press release on last month. Galaxy cluster PSZ1 G311.65-18.48. We'll just call it Betty, okay? So Galaxy Cluster Betty has a really cool feature in it that it has these interesting arcs. There are 4 of them, and they're called the sunburst arcs, okay? And these sunburst arcs contain, let's blow up 2 of them here, right. You look along those sunburst arcs, there are more than 12 images of the same galaxy across these 4 arcs. All right, now the cluster Betty, is about 5 billion light years away. The galaxy that's being lensed is about 11 billion light years away. And at that distance, for the brightness that it probably is, it should not be observable by Hubble. You can't see this galaxy, except that the gravitational lensing not only distorts the light, it also magnifies it. Each image of this galaxy has been magnified 10 to 30 times brighter than it otherwise would be. So these galaxy clusters act as lenses in space to allow us to see yet further into space than we otherwise would be able to. And here we've got 12 different images of the same galaxy stretched out along these various arcs, all right? And you know, there's all sorts of interesting science you can do with that if you can sit and watch it and monitor it and see how the various things go. But it also helps you understand the mass structure of the galaxy itself. So these gravitationally lensed things can produce these amazing configurations that give us very precise information about the structure and shape and mass distribution of these objects located 5 billion and even 11 billion light years away. All right. Any questions? Yes?
Does that mean that if you took away the mass that's warping the space, that the object that's being lensed would just disappear altogether?
Absolutely. We wouldn't be able to see it. okay? Because all 12 images would go down to one image, and that one image would be very faint and not observable even with Hubble. So Hubble, Hubble can't see this galaxy except for that it's lensed, and then when you get its lens, it can see 12 images of it, which is kind of cool. Yeah.
What kind of magnitudes are we talking about on these lens pieces?
What kind of magnitudes are we talking about? Hubble routinely goes down to 26 magnitude on such. This isn't a really long exposure. We can get to 29th magnitude on the really long exposures, but this has got to be mid-20s in terms of magnitudes. Serge is nodding his head. He's an observer. I'm not. So he doesn't know anything about galaxies. There are no stars here, so he's not going to comment. But for the really deep surveys, we can get down to 29th magnitude. These have got to be more like 25, 26, I think. Okay. All right. Well, let's move to our featured speaker. What are you under? What number are we under? 4. Got that? There we go. Our speaker tonight is Serge Dieterich, who started out his academic career right across the street at Johns Hopkins. Then he left us to go on down to Georgia State to do his graduate work, where he worked with Todd Henry and the Recons folks down there who've done some amazing work for, it's almost 20 years, right? Yeah, I've been following that for quite some time. He did a postdoc at the Carnegie Institute, and then decided to finally come here where he belongs. He's been here for 8 months working in INS on the COS instrument. So ladies and gentlemen, to talk about the small stars in our galaxy, Serge Dieterich.
Well, thank you so much for coming tonight. AV, are we good? Can you hear me? Yeah? Okay. So I'll start by saying my very first night in Baltimore was I came for college orientation. It's across the street. And I liked astronomy, liked physics. And so the thing to do was that there was one of these lectures here. So that was my very first activity in Baltimore was attending one of these lectures. I'm not going to say how many years ago, but I do see some young people in the audience. So should you so choose, I hope to be here 20 years from now when you're working here. And that is a real option. This is a very welcoming place. So, okay. So today we're going to talk about something that we don't hear a lot in this institute, which are low mass stars. The reason for that is that most of the research, or virtually all the research I do and that I'm going to talk about, is ground-based. This is just something we don't use space telescopes for that much. So it will be a little bit of a different take on astronomy. So the first third or so is going to be a little bit of a classroom lecture style. We need to get to understanding what a star really is. You've all seen this image. It's one of the most famous images by Hubble. It's the Pillars of Creation. And what we're seeing there is basically the collapse and contraction of interstellar gas to form stars. And once the gas collapses and contracts enough, it gets hot enough to ignite nuclear fusion. A star is born. And the material eventually dissipates, and we're left with free-floating stars like the sun and the 100 billion plus stars that we have in our galaxy. This here is a simulation by a theorist called Matthew Bate out in the United Kingdom. And this is going to give you a computer rendering of what the star formation process looks like. So this is a blob of 500 solar masses. And I'm going to press play now, and that blob is going to collapse and make itself into stars. So the color you see is the density of the material. The lighter, the denser the material is. Here you see the first star just formed. And pretty soon they're going to be all over. See, here goes one, and there's some others forming. So the video is too short, so we're going to play it again. Now that you know where you're looking for in the star formation. And this, I heard the years, this entire simulation covers about the first 200,000 years of star formations, a very, very short time, cosmologically speaking. So that is where the stars come from. Let's look at an individual star right now. There is a characteristic that I like to call stardom, for lack of a better word. What is stardom? What makes an object a star? And stars are actually rather simple objects. You have gravity pulling in, as we just saw in the star formation process. And we have heat, gas pressure pushing down, pushing out. And as I'm sure all of us know from, kindergarten, when you compress a gas, it will get, it will heat up. Compressing a gas causes the temperature to rise. I did not learn that at kindergarten. I actually learned that at Johns Hopkins. So somewhere in between. So what I have here is called a fire syringe. It's a little toy to demonstrate that thing. It is a cylinder inside and a piston. And inside here, I have a little piece of cotton. And the idea is that just like a star can get so hot to ignite the interior, we're gonna try to make things hot enough to ignite this here. So could we have the lights, please? A little fainter. This only works about 50% of the time, so I'm taking my chances here. So, sometimes we can get 2 out of it. No, that was a 1. But basically what we just saw here is that if we get things enough, we can get fires, and in the case of stars, we can get nuclear fusion, get so hot. In this case, thankfully it was not nuclear fusion, otherwise we would not be left for the Nobel Prize ceremony. So that is what the sun is. It is an equilibrium between gravity pulling in, heat pulling out. That's what all stars are. But it turns out that the result of that process is very specific. It turns out that the result of this balance only allows for very certain physical conditions. This here on the left is something called the Hartman-Russell diagram. I like to think about it as the periodic table as stellar astronomy. If you understand this diagram and how stars move in this diagram, then you basically understand most of what there is to know about stellar theory. Today, we're going to be focusing on the part there called the main sequence, the main streak across the diagram. The ones on the upper right are what we call the giants. They're very old stars. And the ones on the the upper left are the giants. The ones on the lower right are the white dwarfs, which are dead stars. We don't care about those today. We're gonna be focusing on the main sequence that is these stars that are in their adult phase. They are in this equilibrium phase. The way this diagram works is that the higher up you are, the hotter and brighter you are, and also the higher mass that you have. So stars up there have 30 or 60 times the mass of the sun. And here's the sun where? Here, right in the middle of the diagram. And then the very tiny stars that we're going to be talking about later on this end. Interestingly, this axis here, the temperature axis, is inverted because astronomers do not like to do things simpler. So this is hot and this is cold. The real reason for that is because it was originally a function of wavelength, blue having a shorter wavelength than red. But now we just plot it as hot and cold. So if we get these stars in the main sequence and we look out into space, we look into our solar neighborhood, what do you think we'll see as far as a stellar distribution? I mean, we often say that the sun is an average-sized star. But does that mean we're going to have just as many massive stars, or as we have little stars, or how does that distribution work out? The result is actually very surprising. We're going to do some abstract art now after I grab my water. I apologize, my throat is very dry, and so I will be taking little stops like this. This is what we call the Recon's marble diagram, and you'll see why in a minute. Let this star here represent the sun, both in its size and in its color. These here are the planets of the solar system. So you see how tiny they are compared to the sun. Now, we're going to add to this diagram the other types of stars within the distance we call 10 parsecs, which is about 32 light years. So imagine our solar neighborhood out to 32 light years. We'll get more to the explanation of the parsec later on. So the first thing we're going to do is we're going to add those dead stars called the white dwarfs. They are tiny. They are about the size of Earth. And here we have about 20 of them. O and B stars are the massive, most larger stars in the universe. We don't have any of those in the solar neighborhood, and it's probably a good thing for life. Next comes the F stars, which are also very massive, but not as much. We have 4 of those. They shine very, very white. They're this hot white shine, and you see they're about 2 times or more the size of the sun. I'm sorry, those were the A stars. Here we have the F stars. So you see the numbers are getting a little bigger as we go along. Those are the solar type stars. The sun is a so-called G-type star. Smaller than the sun, we have the K-type stars, and you see we went from 4 to 6 to 20 to 40. So as we're going smaller and cooler, things are really picking up here on size. Now I'm going to add the M-type stars, which are the smallest types of stars that form. 246. 70% of the stars in our solar neighborhood, and by extension in our galaxy, are very low mass stars with masses anywhere from about half that of the sun to about 7% the mass of the sun. So chances are, if you were God and you closed your eyes and you reached into the galaxy and picked up a random star, it would not be our average sun. It would be an M star, which these stars are, very small. We're going to talk about just how small, and very cool, but they're also very long-lived. So they are perhaps a good place for habitable planets. Perhaps. There's debate on that. So let's go back to this cylinder here. Earlier, I pressed it enough that we had what we pretended was nuclear ignition inside. It was not, but we pretended that. What if I pressed this down, but I was not strong enough? I did not have enough gravity to get to that point of nuclear ignition. It'd still get hotter. In fact, touching this right now, it is hot just because of the fact that I compressed it. But you may remember that tap I gave on it was quite strong to make it ignite. So enter in the brown dwarfs. The brown dwarfs are failed stars. The brown dwarfs are remnants of the stellar formation process when the cylinder basically did not get all the way down for nuclear ignition. The thing to remember, the important thing is that compressing it still made it hot. So they're not necessarily cold objects. They're not like the white dwarfs that are just, floating stellar cadavers, basically. That is not my term. People actually use that term, stellar cadaver, as gross as it may sound. So electron degeneracy pressure, basically gas pressure, solid pressure, stops the contraction before nuclear ignition happens. You do have this burst of heat in the beginning, but there is no nuclear fusion. So they start very hot, and then they just cool down forever. This image here, the one on the right taken with a ground-based observatory, the one on the left taken by HST in 1995, was the discovery image of the first brown dwarf. These objects had been theorized ever since the 60s. But then in 1995, David Golomowski, who now is a scientist here, he was a graduate student at Johns Hopkins at the time, was able to pin one down and show that they actually exist. In this case, it was in orbit around a much more massive star. The brown dwarf is this. It's the tiny one. And we know now that most of them are actually not in orbit around other stars. They're just free floating, just like stars are. So, and they get to be really small. They get to be about the size of Jupiter. And their radius is actually mostly constant, doesn't vary much. But the weird thing about them is because of their internal physics, when you put more mass into them, they actually shrink. They get more compressed. So they're very weird objects, and we still don't fully understand them. They are difficult to study because they are so faint as well. Let's look at the bottom here first. Those are just artist conceptions of what these objects would look like. An M star is one of those very small stars that I mentioned, would be sort of a yellowish, reddish, orangish color. We think that they have a lot of spots on them. There's the bands of spots here. And then for the brown dwarfs, we classify them in three different letters of the sequence. We have the so-called L dwarfs, which are hotter brown dwarfs. As they cool down, they turn into T dwarfs. And then eventually they become very cold objects, almost the temperature of the Earth, called Y dwarfs. Letter Y, not white. Where do these letters come from? I know the person who picked those letters. They literally opened the index of an astronomy book and saw which letters were left. No, it is a true story. Those are letters not used for other things in astronomy. So there is no logical sense to them. The L dwarfs is what we're going to be focusing on for the rest of the class. The L dwarfs are really a mix of different things. Depending on the type of object, an L dwarf could be either a very, very young planet in a star that's only a few million years old. It could be a very low mass star, an object in which nuclear fusion does happen, or it could also be a young brown dwarf. So the question is, if we have this overlap of objects, how do we distinguish them? How do we know where the stars end and where the brown dwarfs begin? That is actually the science question for this talk. That is, this was the topic of my PhD thesis. It's what we're going to be addressing here. I'm going to read this question in a few different ways. Now, you don't have to read that because you've read it, but another way of saying this is, what is the smallest star? I talked about the property of stardom, which is basically an object that enters the main sequence and burns, fuses hydrogen. How small and what are the characteristics of that object? How low in mass can we get? I mentioned earlier that the HR diagram is the periodic table of stellar astronomy. And if you're going to know anything about a star, you need to first understand how it fits in the HR diagram. So that is what we're going to do here. We're going to place a bunch of brown dwarfs and a bunch of very low mass stars without knowing what they are a priori on the HR diagram. And then we're going to see if any patterns come out. When I was talking with my advisor, Todd Henry, and we were thinking about how to do this project, it's like, yeah, let's just place them on the HR diagram. And I was like, well, what if, they're just dots in the diagram and nothing comes out? It says, there is no such thing as putting something in the HR diagram without finding something about it. It is a very useful tool. So he said, just put those dots in the HR diagram and something will come out. Some pattern to distinguish them will come out. So what do we need what sorts of observations do we actually need to place a star in the HR diagram? The horizontal axis is all about color, the color of the objects. Bluer objects being hotter objects, redder objects being cooler objects. The brightness axis is a combination of how intrinsically bright an object is and also how distant it is. You don't know the distance to stars a priori. You don't know if it is something very large and bright right next to you or like very far away, or if it's, like a firefly that happens to be flying right in front of you. So getting distances to those objects is going to be a major part of this observational effort. I'm going to skip this slide. So I was thinking about what to actually present as far as the observation goes, and I thought okay, well, I could bore these folks with a lot of mathematics and all things like that. Or we could talk about something much cooler, which is observatories. As I mentioned earlier, because of the nature of this institute, we don't get a lot of ground-based astronomy here. So I'd like to take a break from the science now and very quickly tell you what observatories are like, because they're really magical places. They are truly wonderful places. If you ever have the opportunity to visit a professional observatory, I highly recommend it. This work was all done in Chile. It turns out that having high mountains right next to the ocean makes for very stable atmosphere. The places like that are California, which unfortunately is light polluted, Hawaii, which is another very good observing location, and the capital of observational astronomy actually is Chile. It has all major observatories, or all major institutions, ground-based observing, have observatories in Chile. So these are two of the telescopes that I used. These are some images from Cerro Tololo Observatory. That is the U.S. National Observatory for the Southern Hemisphere. So the U.S. actually has a partnership with Chile. U.S. goes there, pays for everything, runs for everything, and Chile, as the host for welcoming us, gets 10% of the time on the telescopes. So Chilean astronomy is actually very active because they have 10% of the resources from really all over the world. All countries are putting those telescopes there, and they don't have to fund any of it. They just get it for being good hosts. This is the top of the mountain. It is at roughly 8,000 feet. The top of the mountain is basically chopped off. And there you have the several telescopes. There are about 20 or so telescopes in this observatory. This telescope here during graduate school was home away from home. I actually had a box that I left there with my toothbrush and things like that, so I didn't have to carry it because for about half the year I was there. That's the image of a typical meter class telescope. So when we talk about the sizes of telescopes, we're talking about the diameter of the primary mirror. So when we say a meter, it's not length, it is, the eye of the telescope. And one of the really cool things about these small telescopes is that the astronomer still gets to use it for him or herself. You still get to actually press the buttons and tell the telescopes where to move. Like I do work here. They do not let me do that with Hubble, unfortunately. But even in larger ground-based telescopes, the telescope will itself be controlled by an engineer, the telescope operator, and then you will be controlling the camera at the end of that telescope. In this telescope, if it breaks, it's my problem because I'm the only one there. I have to be able to do everything. Just another pretty picture where this is looking towards the Andes, so towards Argentina and the back of those mountains. This was summer. If it was winter, it would be all covered in snow. Going a little bit further north, this is an observatory called Las Campanas, where I did my first postdoc. These are panoramic images, but you can see that it is above the clouds. Most days you will wake up and you will look down at the clouds. And it's a wonderful experience just to be in a place like that. And you look in the satellite image and you say like, oh, it's cloudy, we're not going to be observing tonight. And then you have to realize, yes, it is cloudy, but the clouds are below you. So this is another image of a typical meter-sized telescope. Again, the telescope that, it is great for training students because in order to use a telescope like this, you actually need to know where the sky is. Like you need to know where your star is and which way you're pointing. Like you ask people who use Hubble, is your target in the northern hemisphere or in the southern hemisphere? Well, Hubble covers both hemispheres every 90 minutes. I mean, why would you care, right? So it is a connection that you get to nature, to both Earth and the sky, that you just don't get with space-based astronomy. Space-based astronomy is, of course, much more powerful, but it's not as fun. Okay, I just said it. So these observatories are like small cities. The people who work there are usually there for exactly a week a week on, a week off. They work on shifts. And at any time, you may have about 100 people or so working there. This is looking down to what we call the lodge. This is the dining area and all the dorm rooms. And this is basically where the party happens. You know, like we're saying this is a geek fest. Well, we don't have anything on these observatories. I mean, imagine going there, being away from family, away from everything, and just with your friends, eating, talking, and observing, and not really worrying about the results too much because you're going to do that when you get back to your office. So it is a very fast-paced life, but it is it's a lot of fun. And in this case here, those were all my friends who I usually only see when I go to the observatory. So it's just a very inspiring place like that. We do not use gasoline or anything like that. We use coffee. Whenever you see a coffee machine, there's going to be two of them, because if one of them breaks, the observatory shuts down. So, you know, it can be challenging to shift your schedule. You're usually coming from a 10-hour plane ride, and then, you know, you're shifting to a night schedule, and you're dealing with altitude, too. This place is about 3,000 meters high. So you do need the coffee to get going. This is what a typical control room for a small telescope would look like. So what we're seeing on the left there is inside the dome. And what we're seeing on the right here is under the dome. Very few astronomers, even ground-based, are actually going to look through a telescope eyepiece anymore. You only do that when the telescope has lost its tracking and you need to find a bright star to align it. All the science is done through computer images. In that sense, it is very much like space images. And another cool thing about these small telescopes is that it's easier to get the time. They're usually undersubscribed, so you have a lot more flexibility what you want to do with them. And since I had like over 100 nights on this telescope, every now and then I would allow myself to do some fun. So this is an image of the Sombrero Galaxy, and I said after a 10-night observing run that had gone really well, I said, like, you know what, last thing I'm going to do is save half an hour to myself and just do a pretty image. So I did that. And again, on Hubble, they don't let you do that. So I see by the age here, the crowd, that you're going to laugh at me, right? And just as I was leaving, they said, like, oh, by the way, all the cars in the observatory are stick shifts. And so this was in a lunch table. And half of us were American, half of us were European at the table. I asked everyone, and the division was stark. All Europeans said that I had to pay an instructor and get a week's worth of classes before I would go. And the Americans were like, just go, you figure it out. And me being the American, I figured, like, okay, well, I will learn to drive the observatory car on the fly. And this is what happened. So this is the very first impression I made on the observatory. And they still asked me back, so it was good. No one was hurt. I was actually not in the car. I was pushing the car, and the car started, so yeah. This was not a good night for observing. This was a very pretty sunset, but we call sunsets like this consolation prizes. It's like, okay, well, we're not going to observe tonight. It might as well be pretty. This little guy is called a vizcacha. It is a relative of the chinchilla, and it lives in the Andes. It is about this big, so it's kind of like a big bunny with a squirrel tail. And the cool thing about them is that they actually watch the sunset. They live in these crevasses in the rocks, and they come out for the sunset, and they will just stand there. I mean, who knows if they're actively watching it or not, but another nice fauna that we have there is, this is a guanaco, which is a wild llama. So, and this is actually a video, so we'll play. It's my neighbor right outside my dome. I came out one day and there he was. So again, one of the things that really fascinates me about astronomy is the Earth to sky connection. You know, we're in this place, you know, dirt roads, rocks everywhere. Our neighbors actually don't have electricity. They're ghost herders, goat herders, and yet here we are, you know, like reaching out to the stars. I think that there is something quintessential about bringing the two together in the observatories. And again, if you ever have the opportunity to go to a professional observatory, most of them will offer tours. Just call them up. I highly recommend it because it is a really nice experience. But break's over, back to the science. So I mentioned earlier that we needed to know both how bright those stars are and the distances to these stars in order to put them in this axis here. Distances are a little bit more fun than just brightnesses. So let's talk a little bit about how we get distances to stars. You may have heard this before. It's a technique called trigonometric parallax, and it is just simple geometry that goes on it. As Earth moves around its orbit, our line of sight to a nearby star changes. We're in this point in the orbit, and we're looking at a nearby star. The stars in the background that we're going to see are going to be slightly shifted. And again, we are moving. The stars themselves are not moving. This is where the definition of this funny distance unit called a parsec comes from. A parsec is the distance at which a star will have a parallax wobble equal to 1 second of arc. 1 second of arc is basically, where's my wallet? Sorry, should have kept it, but if you have a credit card and you look at this thickness from about a football field away, that is about 1 second of arc. So if you were in a football field away and my credit card would be doing, no, barely moving, that is the movement that you get at a star 1 parsec away. But better than talking is doing. So now we're going to do your own parallax measurement. And for the people online, I apologize that this will probably not work as well as it does here in the audience. But so now, for the beginning, what I'd like you to do is extend out your finger and pick any number in the ruler, cover that number with your finger, and then blink your eyes. Look at it first with one eye and then the other. And you will see that the position of your finger moves. Of course, your finger is not moving. It is just this line of sight thing. Now, bring your finger closer. Like put it on your nose and do it again. And you'll see a much bigger movement. Well, that is basically how we measure distance to stars. There are other methods, but they are all calibrated based on this method. This is the only direct method. Everything else uses this as the base. So, of course, if it was as easy as looking at our finger, like life would be easy. It turns out that this effect is right at the edge of what we can measure with telescopes. Parallaxes worth measuring are extremely small and convolved with many other optical factors. You need very good cameras to do this. So this is me measuring a parallax remotely. This is my office in Washington, D.C. when I was a postdoc. This is the telescope in Chile. And what you see on the bottom left image there, this gold bottle here, Dewar, is actually the instrument, the camera. All astronomical cameras work at very cold temperatures that increases their conductivity and reduces noise. So they all work in dewars or bottles filled with liquid nitrogen. So, and in Chile, there will be a telescope operator, an engineer that is communicating with me through Skype and is moving the telescope, and I have the camera controls through the internet. And so one of these stars here is the one I'm trying to measure the parallax for, and all the other ones are the reference stars. They are the background stars that are going to be the numbers in the ruler there. All right, I see we're going low, so I'm going to skip a few. So what are the results once I put the parallax together? I mentioned that between this slide and the previous slide, a PhD thesis occurred. That's because I don't actually want to bother you with all the mathematics of how we go from those observations to actually having an HR diagram. But this is the new HR diagram that I made as a result of my thesis. Everything we're seeing there is here in the last box. So there used to be about 3 stars there, and put a lot more. Well, remember my advisor had told me, like, put stars in the HR diagram and a pattern will come out. I don't see no pattern. I mean, it doesn't look much better to me as it does to you. It is kind of a blob. That is because we're looking at it in using the wrong variables. It turns out the HR diagram is also a tool that will tell you the radius of stars. These perpendicular lines here, or the slanted lines, are actually radius lines, lines of constant radius. So I'm going to shift the axis here. And now we have a diagram that is in units of luminosity, so how bright. Objects over here are brighter than over there. And radius, smaller and bigger. And I'm just going to let you stare at that for a few seconds and see if you can figure out any patterns there. So what I'm seeing is that we have a sequence that is coming down. That is the main sequence we talked about. And then we reach a minimum radius at that point there. And then we jump back to cooler or fainter objects but higher radii. Let's go back to the toy star here. We mentioned earlier that if a star is fully compressed, it will ignite nuclear fusion, and it will have a source of energy. And therefore, even as a fully compressed star, it will be able to survive as a star. For brown dwarfs, in order to generate energy, they need to be in the compression phase. They need to be coming down. Once they stop contracting, their energy generation stops and they cool down. So the interpretation that we did here is that these are fully contracted stars, and these are the brown dwarfs because that are still shining because they are in the process of contraction. Because they haven't finished their contractions, they're bigger. They are a little bigger in radius than the stars. That is something that theory predicts. So we were able to pinpoint that star to mass 0523. That should be a minus 1403, as the smallest star that we know of, the end of the main sequence. And here's an image of that. It is serendipitously almost exactly the size of Saturn. So imagine, stars are such diverse objects that you can get stars of planetary size. Not Jupiter, but Saturn, which is slightly smaller than Jupiter. Not mass and density. Mass and density are much, much higher than planets. Its luminosity is about 1/8,000th of that of the sun. So, very, very faint. And if you're an amateur astronomer, you could find it in Lepus, right under Orion. Now, this image here has a funny story. When this paper came out, I got a call from Sky and Telescope. And they're like, we really would like to see the image of this star. It's like, oh, sure, no problem. So send me your email. And I emailed them the discovery image from the telescope. And then they were like, oh, no, we meant a color image. Do you have a color image? It's like, no, that's not what we do. Like, we don't work in colors. Just don't have a color image. Well, we really want a color image. Okay, well, let me see what I can do. So the criteria for making this image is that no matter how I played with the RGB values, the sky had to remain dark. And so that's how this image came about. It is a fake color image, but you see the star is a little redder, as we expect it to be. And the sky is not some funny purple color that came out. So. Okay, so I will skip a little since we're late into how we actually measure masses for these stars. It turns out that masses can only be measured if you have two stars in a binary system. Gravitational attraction is a function of mass, and it's really the only way to tell how massive the stars actually are. So one of the predictions that we made with that star is that that star turned out to be much cooler than, colder in temperature than what some of the models were predicting for very low mass stars. And so we made a prediction that if we were to find the mass difference between stars and brown dwarfs, it should also be different than what the mass that the models were predicting. So we found this star called Epsilon Indi. It was a binary system. And we measured its orbit with, again, ground-based tools. And then when we combined the orbit, the theoretical orbit, to the image, we were able to get masses. And the mass that we got was a mass of 75 Jupiter masses for brown dwarfs, when models were saying that those masses should be anywhere from 70 to 73 Jupiter masses. So this is the discrepancy between models and theory that we were investigating, and it's a challenge for the formation scenarios and for the cooling scenarios for brown dwarfs. And we're still investigating why that is, and why is it that we don't really understand brown dwarf evolution at this point, and why is it that when models are telling us brown dwarfs should be one temperature, observations are telling us a different temperature and a different mass. So that is an ongoing area of study here. I have more on that, but I'm actually not going to show you because we have another neat movie. This is a movie of all stars within about 100 100 light years or so from us. It is made by a friend of mine who also works here called Dieterich Rito, and he is an artist at computer graphics. So what we'll see here is an animation going out from the sun, looking at the nearby stars, and then going back. No? No? I need to get out of this. So none of that is my credit. Dieterich, who's a software engineer in this building, did this when he was in graduate school. And no, we don't want to see the next YouTube video. I'll put this back up. I guess the next YouTube video is playing. Okay. So conclusions, we know where the brown dwarfs are and where the least massive stars are right now. We've pinpointed one star, and we say that is the least massive and smallest star that we know of. We are still studying them as a population. And is that my music that's playing? I see. Okay, sorry. Okay, there we go. One last thing I wanted to show you. I know we're going over, but so the rules are that you are not allowed to do any of this work in astronomy unless you have a shirt that says you're thinking about it. And so should you like to buy the shirt, here is the link on my website, and you can buy it on cost from the company that did this. So this will be and there's stars in the back to prove that it's about stars, really. Yeah. So that's all I had. I'm sorry I went over a little. Thank you very much.
Questions? First, yes.
So I noticed on one of the last screens it was talking about singles, binary, triples, and
Right.
quads or whatnot. Are the low mass stars, do they hang out with other low mass stars, or are they as likely to be with any other weight?
Very good question. And the answer is that as you go down in mass, the tendency to be binaries decreases. So for the very high mass stars, they're eventually all binaries. When you get to the very low mass stars, there is about 30% binarity. And when you get to the brown dwarfs, it's only 20%.
I heard somewhere that the brown dwarfs will last for 1 trillion years, that they won't burn out because they have formed some sort of equilibrium. Is that true?
So that is true for the very low mass stars, not the brown dwarfs. It's a very interesting point that for very low mass stars, when you reach that equilibrium phase, they're predicted to last longer than the current age of the universe. So no low mass star, no M dwarf has yet evolved to its adult, to its old age. They're all still adults. Now for brown dwarfs, they will be continuously cooling down. So brown dwarfs don't have stability.
Yeah, that was a question that came up online. So brown dwarfs shine while they're contracting. How long does that contracting phase last? Do we have a good estimate of how long they will shine?
Right. So it depends on, the answer to that question depends on how powerful your telescope is and what you consider shine to be. In this phase where they are shining so bright that they're being confused with stars, that is about the first 1.5 billion with a B giga years for brown dwarfs. The real zone of confusion is about 600 million years. Once you get to several billion years, they get very cold and undetectable.
Well, my follow-up question would be, this gives the low mass stars where life can evolve around them because they last so long. The planetary systems would be stable enough for life to evolve. Is that correct?
That's $1 million question. And there are two camps to that. The one camp is exactly what you said, that that they are very good candidates for life because of their stability. They also do tend to harbor rocky planets. We know that. The flip side of the coin is that these stars are not very photometrically stable. They tend to flare a lot. And they tend to emit a lot of X-rays and UV radiation when they flare. And because they are so faint, a planet in the so-called habitable zone would have to be very, very close to the star for it to be warm enough. So it would be very susceptible to those flares. That is actually an active line of research for me right now. I'm trying to understand their flaring rates by trying to get a handle on their spot patterns. Are they very spotted, or are their surfaces more evenly spread out?
Good catch.
How does the fusion of deuterium factor into the life of a brown dwarf?
That is an excellent question. Brown dwarfs are objects that can fuse deuterium, but cannot fuse light hydrogen.
Yeah, make sure people know what deuterium is.
Right. So deuterium is sometimes called heavy hydrogen. It is a hydrogen has a nucleus that's just one proton. A deuterium, or hydrogen 2, has a proton and then a neutron right next to it. So it is twice as heavy, and that extra neutron intermediates the fusion process and makes fusion much easier to happen.
Right, so deuterium fusion happens at a lower temperature than hydrogen fusion.
Deuterium fusion happens at a much lower temperature, and brown dwarfs can burn deuterium, yes. But the thing is that there's so little deuterium compared to hydrogen to begin with that that burst that they get from deuterium burning, called the deuterium main sequence, is very short-lived and not very consequential for the evolution of the object.
If you said it and I didn't get it, I apologize. The question is, what led you to find that little star that you showed us on the screen? Out of all the stars and all the gas and all the things you can see
All
out
the
there,
people,
how
all
did
the
you
gin
find
joints you could walk.
brown dwarf?
So, that is a really important question, because there are more stars out there than we can possibly study. So one of the arts in astronomy is really sample formation. What sample of stars are you going to study? How are you going to design your sample so that it is unbiased and so that it's going to be representative? You can think of polling, like there are those people that do electropolls and get it smack on. It is a function of sample design, how they're designing the sample that they're doing. In this case, what we did is we picked known stars that we thought would be around that temperature range, so that we thought would be on either side of the boundary, and we said, let's extrapolate enough to both sides that we know that we'll have a representative sample. What does not factor into our sample is their abundance. So we just picked basically one of each color. We didn't care about the fact that a certain type has many more stars than the other. That, what I'm describing now, called the volume complete sample, is something we're doing only now.
Okay, so we had a question related to that. You showed very clearly that the minimum size of a star is about 9% the size of the sun.
Right.
But it wasn't obvious from your graphs what the mass of that object would be, and I assumed it was like 70 Jupiter masses, but is that correct?
So yes, the number we got, and I actually did skim very quickly through this because we were running low on time, but the number the models are indicating are close to 70 Jupiter masses. We're getting numbers closer to 75 Jupiter masses.
Okay,
so
and
we believe.
what is that in solar masses? Because I didn't have that in my head.
This is actually a very convenient conversion. Just add 2 zeros.
Good.
So 0.07.
That's what I remember.
Jupiter is about 1/1000th the mass of the sun.
Good. Okay.
I think my question got answered. My question was, what would it take for Jupiter to become a brown dwarf? Why is it not a brown dwarf?
Right. So there are actually 2 ways that we define brown dwarfs on the lower limit. One way is the question we had earlier, whether it burns deuterium or not. In that definition, the models show that it will take about 13 times the size of Jupiter, so an object of 13 Jupiter masses would be a brown dwarf. The other definition, which I think is being more favored by the community now, has to do with whether it formed as a planet or whether it formed as a star. If something forms in a circumstellar disk and is a leftover from stellar formation, then it would be considered a planet regardless of its mass. And if it formed, like we saw in that first slide, when by cloud collapse, then it would be considered a brown dwarf regardless of its mass.
Got a question over here.
Ready? Hello. Just a quick one. How much is the Webb telescope going to help you on this?
It is going to help substantially because it is an infrared telescope, and all this is being done in the infrared. One of the projects which I'm going to propose to do, and I'm really excited about, is that these objects have a lot of water vapor in their atmosphere. And from Earth, we have water vapor in our atmosphere. So from a ground-based telescope, it becomes very difficult to deconvolve the two signals. Hubble cannot reach that far into the infrared to do it, but Webb is going to do it. So I hope to get the time.
All the way down to the brown.
Yes. And as far as the sensitivity goes, it's not going to be an issue for Webb at all. I mean, it isn't for Hubble. These are powerful telescopes.
So a related question is WFIRST with its incredible field of view and Hubble resolution, is it going to go far enough in the infrared to really do much on stellar?
Yes. So this is a really interesting, and we actually made a case for WFIRST for this, is that this smallest star that I showed here was 10 parsecs away, or thereabouts. I think it was 12 parsecs. WFIRST would be able to pick up that star in a crowded field in a full quadrant of the galaxy. So we're talking about 1/1000th of the galaxy. WFIRST would be able to do, a fourth of the galaxy in survey mode. It wouldn't even have to be pointed observations. So it would be a very powerful tool for this.
Yeah, if you don't know, WFIRST has, 300 million pixels per observation, but with Hubble resolution, and it is an infrared telescope, but it's a survey telescope, so it's gonna increase the data rate by a very large amount around here.
Well, some of the time is going to be dedicated for PI searches as well. So, yeah.
All right, one last question. Anybody got it? Okay, if we don't have a last question, let's hold on. We're not going to thank our speaker just yet. We have to remind you that next month we will probably have construction in the lobby. Look for the signs to see where the entrance to the building is. Second thing, we're January 14th, the second Tuesday, all right? Not the first Tuesday, the second Tuesday. I'll be in Hawaii on the first Tuesday. You're welcome to come join me there, but that's where the AAS meeting is. And finally, let us thank Serge for a wonderful talk.